Oh, good morning. Nice, cold, chilly day. Today I want to pick up. Is there an echo in here, or is that just the?
Can you hear it up there?
Must be. I don't know. It's okay. It's better.
That TV was rather loud.
Okay, great.
Is that okay?
Yeah. So, what I want to talk about. Oh, can you pull up the whiteboard, the projector? Look at the data structures we were looking at, and then do some algorithms on those. So, but project 0, suddenly it's dark. Is it too dark? No. Can you read this? Project 0, download the Sparse package and compile and run the demo. I'm not going to grade that. Just start playing with it, because on Friday I'll assign the first project, and it'd be handy if you could have that tried out. So the data structure we looked at then for a sparse matrix that we'll use repeatedly in this course is over here on the projector. Now, all these notes, by the way, these slides are on my webpage. Not the Sakai or Seikai, how to pronounce it, but there's a link to there from my personal homepage in the department. And from there you can see at the top line is the class page, and then under there will be these notes. So here's an example matrix, and here's the two formats. Here's a triplet form, just lists of, here for instance is row 1, column 1, value 2.9. So that's this entry in here. And these are in some arbitrary order. Doesn't matter which order. There happen to be no duplicates here, but we can handle those if we need to. And then here's the compressed column form with the column pointers and the row indices, but no column indices. And what I want to do today is show you an algorithm for translating between these two, back and forth. But just to pull up the data structure, then it's got these three pointers to these three arrays, the two integer arrays and the real array, and then these four scalars. And this NZ then tells us two things. It tells us the number of entries in a triplet matrix, if it's a triplet form, or it's -1 to denote the fact that this is not a matrix in triplet format, but it's a matrix in compressed column format, in which case P is the column pointers. But if NZ is greater than or equal to 0, then P is of size the same as I and X, and it's a triplet form. So I use this one wrapper to handle both of the data structures. And then this was the Gatsby function that we looked at. The Gatsby stands for generalized AX plus Y. So it's taking Y equals Y plus A times X. And I want to go through a few of the mechanics of the code, because you'll see this over and over again. This is the sparse matrix data structure, pointer to this object. I'll just use regular double pointers for dense matrices. So these are two vectors. I don't have to pass in the size of these things because the size is implied by the size of the A matrix. And of course, if you pass in the wrong size of things will break, and Seed won't check that for you. But one thing I do, so I don't do exhaustive checks on my data structures for each function. But one thing I do, you'll find repeatedly, is this kind of statement right here. First of all, I check to see if I've been passed a compressed column matrix. That is, first of all, the A pointer has to be non-null. And what this does is it protects from memory faults of the caller. So if the caller ran out of memory and couldn't create the matrix A, I won't get a seg fault here. I'll return a false, return 0 for failure. And same thing with X and Y. X and Y have to both exist. And I'm expecting, this is also really an executable comment. It's telling me that I'm expecting a compressed column form, which basically says that the ANZ has to be -1. So I can't work on it. This algorithm doesn't work on a triplet form matrix. And then the next line of these functions is usually some kind of thing like this, where I extract out the contents of the sparse matrix I want to work on. And so I get the n, the dimension, the AP, AI, and AX arrays. And then the rest of this then is the actual algorithm. So this is, for these first 4 lines are just bookkeeping. And then the next few lines here are the actual algorithm that I talked to you about yesterday. We go across for j equals each column of the matrix. And then this is a loop you'll see over and over and over again. So this is iterating across all the entries in a single column j. And it's getting a row index. So this is y of I. AI of p is the row index I. And this is the value aij. Here, ax of p then is the numerical value. And then I return success as positive, or as a 1 for true and 0 for false. Normally I won't belabor all the code details, but I will be looking at code. I mean, I'm not just going to look at pseudo algorithms, the pseudocode. And the reason I like to do that is because there are a lot of details in the code that if you just write pseudocode, you could ignore. And if you do that, you get the deadly n squared, right? It's very easy to write the pseudocode in a generic way such that when you suddenly actually think about the code, suddenly your algorithm becomes n squared time. So it's very important to look at the details. Otherwise, you can easily make mistakes. Believe me, I've done it. Not anymore, but I used to. My students do all the time, right? Okay. So because we're looking so closely at code, we're looking both at code and algorithms. Again, they're very closely tied together in this topic. I want to look at some basic utilities. I create some wrappers for the malloc and free and realloc from C. One thing I do with malloc here is I make the calling sequence similar to calloc. So malloc and calloc are then replaceable, or interchangeable. Malloc also, I require, this is just taking the max of n and 1. I enforce the case that I'm going to always allocate an object of size at least 1. That way I can check for failure uniformly by saying, oh, did I get a null pointer out? I don't want to, because you can have a sparse matrix with no entries in it. But you think about checking for failure. Okay, if I malloc as something of size 0, do I want to keep track of the fact that, oh, well, that null pointer is okay? Well, that's a pain in the neck to do. It's a lot easier for null to denote a failure to allocate something always. But it's reasonable to have a sparse matrix with nothing in it. Okay. So that's why I force the allocation of at least 1 unit of space. Same thing with calloc. I force this. One thing I do with free, and this is a very simple thing to avoid memory leaks. First of all, I'm leery about freeing a null pointer, so I only free something that's non-null. And then this looks rather odd. I return a null pointer always. And the reason I do this is because then I find this a more convenient thing to do. Then if I have an object I want to free, I do x equals free of x, or cs free of x. And this assigns x to null so that if I try to free it again, it won't be freed again. So the double freeing of a pointer, which is a problematic memory leak in C, then is avoided. So the other advantage about wrapping these, putting wrappers around malloc, calloc, free, and realloc is that if you want to use different memory managers, you can just replace it in these 4 places. You don't have to go through the whole code. Realloc is also a very strange beast in C. I don't like it at all. So what I do instead is first again I enforce the fact that the size of the object the new object is a size at least 1. Okay, and then if the realloc fails, it returns a null pointer. But you don't want to lose track of the space that you originally had. That's one thing I don't like about the C realloc. It returns null on failure, but the object still exists of the old size. So I keep track of the 2 pointers. I have the old one and I return the new one. And I return the new one if it succeeded, but if it failed, I return the old pointer. So I can just say, if I want to make x bigger, I can say x realloc x. with the correct size, I can do that, and I'll always have x pointing to whatever object I still have. Okay, it may be bigger, it may be not be bigger, but I don't want to worry about the fact that, well, okay, when I'm done, I have to free x or not. Okay, memory leaks are a serious problem in most codes. Even commercial codes have memory leaks, but mine don't. And so because I'm careful like this. Sometimes it's not a critical failure if realloc fails. Sometimes you say, well, look, I want a space that's going to be this big, but oops, I wasn't able to do it. Well, sometimes you can live in this much space anyway, maybe less efficiently. So a failure to realloc a space larger is not necessarily a fatal flaw. So that's why I still and even if it is a fatal flaw, you want to free the old object on cleanup, right? You got to if this returns a failure, you've got to then I got to free x, and I don't want to lose it. So that's what happens on realloc. So these are just some very simple malloc wrappers to make malloc and realloc work a little more sanely. Now, with those 4 wrappers, I can take my C-sparse data structure and do things like allocate it and free an object. So this is going to create an empty sparse matrix for me. First of all, I want to allocate the header, which is this C-sparse struct, and set it to 0. So it's a calloc. And then I want to return a null, of course, if it fails. And then I need to populate this matrix. And I want to go through and fill the row and column dimensions. Get the here's the requested number of non-zeros that this matrix can hold. I'm going to then allocate either a triplet matrix. There's a flag here that says, hey, are you allocating a triplet or compressed column matrix? So that A and Z is then set accordingly to 0. So there's no entries in the matrix if it's a triplet form, or it's -1 to denote that it's a compressed column form. And then I have to allocate the PI and X arrays. And so there's a malloc here of either of size NZ max or N+1, depending on whether it's a triplet matrix or not. And then there's a malloc of the row indices and the malloc of the numerical values. But sometimes the numerical values are not needed. Okay, there are cases when you create a sparse matrix, but you're only interested in the non-zero pattern. You may be doing an ordering method that says, well, let's order the matrix to reduce fill-in. That doesn't depend on the numerical values. But you want to create a copy of a matrix to do some kind of ordering on. You don't need the values, and so I allow for the AX array to be null here. So that's a flag values, whether or not you're allocating the numerical values or not. And if you're not allocating it, then this AX array, AX pointer is null to denote the fact that this is a pattern-only matrix with no values. And it's very important, it's very easy to come up with have memory leaks here. Suppose one of these fails. Okay. Well, if one of them failed, but one of them succeeds, you've got to free this thing that succeeded. Right? Okay. So I go through and allocate all 4 objects. Actually, four of them here, 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 and here. Now this one I have to check first because there's no place to put the pointers if this top one fails. But at this point, only one thing has failed, so there's nothing to free. Here, 3 things have been allocated. If something fails, in particular, if AP is null, or if AI of null is null, or if you're asked for the values and AX is null, then I need to free the matrix. Otherwise, I have the matrix, and this is a return statement. So I'm returning either A or null. This SP free is going to free a matrix and return null, because CS free returns null. So this whole allocation here is either going to succeed and everything is going to be present, or it's going to fail and return null, and nothing that was tentatively allocated will be allocated because the SP free will free whatever components of the matrix have been allocated. So here this might be a null pointer. Any of these might be null. That's okay, because you know that my free wrappers are not going to free a null pointer. If the matrix is already freed, there's nothing to do. This is used everywhere whenever we want to delete destroy a sparse matrix. If it's already null, then do nothing. Otherwise, free all the contents and then free the header and return null. So there's allocating and freeing a sparse matrix, and it has to be done. These sorts of things have to be done very carefully. One thing you're going to find as you write code that you'll very frequently come across memory leaks. It's likely that as you write your projects, you will have memory leaks in your code. Now, MATLAB is very forgiving. All of your codes will be driven through MATLAB. So you'll write in C, but you'll have MATLAB interfaces to the codes. And MATLAB, when you call malloc and free and realloc inside a C function called by MATLAB, MATLAB is rather nice. When you return, if you've forgotten to free something you malloc, MATLAB frees it for you. Okay, so in some ways I'm being more persnickety, more careful than I need to be, but this code is also used in a standalone way as well without MATLAB. So that's just some of the mechanics, but they're very, very carefully designed mechanics to make sure the things work smoothly. Then one other thing that I want to be able to do to a matrix, and this is this idea of, well, gee, how big is your matrix? How many non-zeros are in your matrix? Well, what if you don't know ahead of time? What if you create, say, a column pointer of size n plus 1, and you say, okay, look, I've got this many non-zeros in my matrix. And then you say, whoops, that's not, and you use it. You've got empty space here. And then suddenly, oops, my matrix is becoming has more non-zeros than I expected. Things are changing dynamically, and now we need to reallocate the matrix. Or what if the opposite happens? What if you think your matrix will have this many non-zeros, but some large number, but in fact the actual number of non-zeros that you need when you're done is something smaller? That happens as well. So you want to trim off that extra space. And so this function sprealloc is going to do that for us. It's going to change the NZ max of a sparse matrix. All right. Now, this is rather a little bit gnarly, or difficult. It has to be done carefully. First of all, if I don't want to, I'm not returning the new matrix. I'm just changing this existing matrix in place. So if it's a null pointer, I can't reallocate anything. So I return a failure, which returns 0. 0 for failure. If then I have to find out, well, how big is the matrix anyway? How big? What is the current value of the number of how many let's see, let me back up. What this statement is doing here, if NZMax on input is telling us how many non-zeros do we want to have in the matrix. If it's positive, so suppose it's 1,000, then it says, well, look, I want to whatever size the matrix is now, I want to specify that it will be able to hold 1,000 non-zeros. Okay. But sometimes I want to say, well, just trim off the space, make sure it can hold as many non-zeros as currently exist in the matrix. In other words, make NZ max equal to NZ, the number of non-zeros in the matrix. And that's what this statement does here. If NZ max is 0 or negative, then in fact what I'm asking for, what this code interprets that as is, oh, you're asking me to shrink the matrix, shrink wrap it, make sure that you're going to trim off any extra space and say, okay, make it just this big, however big that is. So get the actual number of non-zeros, and that's what this does. So if it's a compressed column matrix, the actual number of non-zeros in the matrix is AP of AN, the one past the last pointer. So the nth pointer here points to the one past the end of the last column. So that's the number of non-zeros in a matrix. AP of n. In the compressed column form is always the number of non-zeros in your matrix, a compressed column matrix. So that's what this does. Otherwise, we get the actual number of non-zeros from a triplet matrix here, the ANZ. Now what I need to do is reallocate 3 parts, potentially. I need to certainly, in both kinds of matrices, triplet or compressed column, which this is doing both. I need to reallocate the row indices to be NZ max. And so you saw the CS reallocate before. And it's still, if it failed, it's still returning me the existing array. But it's giving me this OK flag that tells me whether or not I failed or not. Then for the compressed column form, or the column pointers here, in the compressed column form, it's a size n plus 1, so I'm not changing it. But if it's a triplet form, I've got to change it. So if A is a triplet matrix, then I've got to reallocate the column pointers, really they're column indices. Then if it's a matrix with values, I mean, this AX array may be null. It may not be present at all. If it's not present, I don't want to change it. It's null. All right. So I'm not changing a pattern matrix to a valued matrix. So if AX is present, then I've got to reallocate that as well. And if things work out, if everything is OK, then I change the size of the matrix and I return the values. Otherwise, I return failure. OK. Now, if that happens, there's some little oddities that could occur here, okay, that I don't worry about. And here's what could happen. Some of these reallocs could fail and some could succeed. So for instance, what could be happening here is that suppose I was able to increase the AI array, but then when I tried to increase the AX array, it failed. Okay. Well, if that's the case, then I don't change NZ max. So you've got these 2 arrays now of different sizes, but the NZ max is still pointing to this size here. So this is space that will never be usable at this point. It's a rather odd data structure. But I return a failure saying, look, I didn't get it. And so the caller can do whatever corrective action he or she desires. But it's a valid object that can still be freed and used. But I wasn't able to get the requested number of non-zeros. But I don't destroy it either. Okay. The existing entries are still there. Yeah.
Which code would benefit from you trimmed before you ran it?
I'm sorry?
Well, this is like reducing the size in the case where you make too much and you wanted to shrink it.
The question is, why would you want to take a matrix and shrink the space?
Yeah.
We'll see that I'll use that quite often actually. I will use it in when I want to take a matrix and remove duplicate entries. Okay. In the process of converting a triplet form to a compressed column form, what's going to happen is I'm going to have some duplicates that I need to sum up. Well, I don't know how many that will be until I'm done. So I'll have a matrix that's of a certain size. It says, well, let's assume there's no duplicates. And then I'll sum up the duplicates and the thing will shrink to some unknown size. So then I want to trim the thing. The other place it happens is when you do matrix multiplication. You don't really know how, unless you do a symbolic analysis first, which my code does not do, I don't know how big the matrix is going to be until I compute it. So I compute it and reallocate it on the fly. And when I'm done, I want to shrink it to the exact size that it really is. So there's lots of places where, well, we have a bound on how big the output matrix is going to be. We're producing a sparse matrix. We have a bound on how big it can be, and I say, look, just allocate that. Okay. And then fill the matrix, and then, oops, okay, now we've got some space left over. Let's trim off the excess. So that's why you'll see very frequently I'll call the code. In fact, if you grep the source code for sprealloc, you'll find this is very often a 0 here. 0 denotes trim. Trim the space to be exactly the size you need. Yeah?
If you're trimming and AI realloc succeeds, but then the AX realloc fails, wouldn't NZ max then be too big and you risk overflowing AI?
Yes, but the trim reducing realloc. Okay, here's that's a good question, and I do worry about that. Let's see on the Actually, I don't worry about that in this code. In my commercial quality, this is commercial quality. In my more elaborate codes, I worry about that fact. And what happens there is if a realloc fails when you're making it smaller, I pretend that it succeeded. Because who cares? You got the space. I tell my data structure that, look, you only have this much space now to work with. And when I go to the free and I say, look, free this object, and here it is, well, free knows how big it actually is. So I just pretend to succeed. I don't do that here. I've never seen a case where making something smaller fails.
Yeah, it's pretty rare.
I can't think of a case where it would fail. Why should it fail?
Yeah.
Right? I've never seen it fail, ever.
I'm so used to having, oh my God, how did this fail?
Right, how could it have failed? I've never seen it fail.
And then it fails.
Yeah, so I rely on that fact here, yes, that making it smaller always succeeds. But actually, let me think here. So if it fails, okay, so let's think about what happens. If it fails to make it smaller, then it's going to return a null pointer, but I'll return the old one anyway. Okay. So this thing is okay. So the question is, though, but I still return a failure. Now here with reallocate, now when I use that, let's see what's going to happen. Suppose I'm doing a trim. Suppose I'm saying this is 0. So I'm trimming the excess space. Then yeah, if it returns a failure, then I only change NZ max. Right, that'd be a problem. You're right. It looks like I'm not accounting for that fact in this code. Yeah, it's a good point. And in the codes in MATLAB, I worry about that very fact, and it's one of those things that it's almost impossible to test for. You have to force testing code like this is difficult. You have to have malloc substitutes that you say in the testing that says, okay, malloc, you can succeed 4 times. On the 5th try, you will fail. And I force it. I pretend to fail. I pretend malloc to fail. People don't test code like that, I don't think. But then their code has memory leaks in it. And then I check to see when I'm done if I freed everything I'm supposed to free. And if I have, then I'm fine. If I haven't, then I've got a leak. Most codes aren't tested so obsessively. I'm obsessive. But you're right. I don't account for that here. Very keen observation. Okay, so now we get into a little bit more theory, although I still have code up here. Oh, for those of you who came in late, don't forget there's a Project 0. Download the code, run it in MATLAB, run the demo. It's not graded, just because on Friday I want to assign the first project. So just get up to speed in actually running the code. Now there's a little bit of nice theory here. And this is this idea, the idea here is a dynamic table, the algorithm, the dynamic table algorithm. The idea looks like this generically. Suppose you've got a list and you don't know how big it's going to be, but you want to append an item to this list and then grow the list as needed. But you don't know how big the list is going to be at the beginning. The question is, how much time does that take? Well, if you did the following, if you had a list and you say, okay, I want to add 1 entry. Okay, let's make the array 1 bigger and put it there. Well, in the worst case, that's awful, right? This is pathetic. And the reason this is pathetic is it's quite possible that you have to make an entire copy of this array and put it somewhere else in memory to add 1 entry. So if this is if you have if you're going from k equals 1 to n, the kth step takes order k time, and so the total time is the sum of k. It'll be basically n squared over 2. In other words, it'll be order n squared to create this list, which is pathetic. Okay. If, on the other hand, and I assume you've seen this notion of the dynamic table, but if you haven't, this is a refresher. Or, no, it's not a refresher if you've not seen it. It's a brief introduction if you haven't. It's a refresher if you have. The idea here is instead of increasing the size just by 1 each time, you double the size every time. So if you start with a size of object of size 1, and you want to then insert 1 entry, then it becomes of size 2, and you have the 1 entry. But there's several ways of doing this analysis with an amortized analysis. Or you could say, well, let's just sum up the total time that this will take. So this will take 1 unit of time. Doing the copy will take 1 unit of time to do the insert and 2 units of time to do, I'll call this 1 plus 1. 1 unit of time to create the array and 1 unit of time to put the item there. When I increased the size 2, I had to take 1 unit of time to insert the item, but I had to take 2 units of time to make the copy. Okay. When I do 3, I'm going to double it in size. So I still take, let me call this, I'll call it 4. It's actually probably going to be 2. No, I should change this. This is 0, 1, and 2. Yeah. This is the time required to copy the old stuff. So this is the time to copy the old stuff. This is the time to add the new entry. But when I get to 4, and I double the thing again, I'm running out of space, then I just take 1 unit of time because I've got the empty space there. And right here. So now I've got just 1 unit of time. But when I add the 5th entry, I have to take time 1 plus 4. 1 to add the 5th entry, but 4 I first have to copy the existing 4 entries to a space of size 8. So then 6, 7, and 8, I have no extra work to do, just 1, 1, and 1. And you can see what's happening now. On the 9th insert, I have 1 plus 8. The 9th through the 16th, I have only a unit of work to do, 1 unit of work. So it's doubling every time. Now, if you sum up the total work here, and you stop at n, okay, you're summing up powers of 2, and you basically get 3n. You get n from this, 1 unit each. But if you add 0, 1, 2, 4, 8, and so forth, the worst you can get is 2n. I mean, if n is, in particular, if n is 32, suppose n is like 33, okay? Or suppose n is 17. We'll do this. If n is 17, I had to make copies of 16 objects at the very last step. If you add up 0, 1, 2, 4, and 8, this adds up to 15, roughly n, or n minus 1, plus n. So this is just less than 2n. So the total of the total work is less than or equal to 3n. And it's certainly greater than n, because I've got n units of work here. So in other words, what this means is the time, the amortized time, the average time, to insert n entries into this data structure, this dynamic table, is theta n. Because it's bounded above and below by n, which is perfect, right? It's asymptotically optimal in the sense of a total amount of time. So the amortized time, if you take the average time per insertion, is 3, which is acceptable. It's a constant. So the average time to insert an item into this list is constant time, which is what you want. Even though any one of them might be big. It might require a copy of the entire array. But since that happens rarely, then you're safe. Okay. So this is the idea of a dynamic table. You're inserting items into a list. You don't know the final size. But you don't want to allocate a huge space because you don't have it. You allocate a small space and double it every time. So the total time complexity is size n. Even though any one of them will be bounded by n, the total time is not n squared. If you just said, well, what's the worst case for any one insert? Oh, it's order n. The nth item, to insert the nth item could take as bad as order n time. If you insert a total of n items, you could imagine, oh, it's n squared total. No, it isn't. This is where the n squared doesn't kill you. It doesn't come up. Okay, the total time is n, order n. It's 3n to be precise. So that's the notion of a dynamic table, and I exploit that here in this algorithm. So what I want to do here is, it's very common when you're creating a sparse matrix that you just create it one entry at a time, and you don't necessarily know how big it is. You're going to want to create it in any order you like. Sometimes what you want to do is you want to say, well, not just insert an entry, but add an entry to the matrix. So I have a matrix here, and I want to say, okay, add to the take Aij and replace it with Aij plus some update. Okay. So in other words, you'll have some loop where you say Aij equals Aij plus some expression. This is a very common way to create a sparse matrix. And of course, if the thing is initially 0, then this is irrelevant. So you can just say Aij equals whatever. And so this addition of entries can be done in an arbitrary order quite frequently. One place where this occurs is finite element methods. If any of you have ever worked with any of those, with a finite element method, you create a sparse matrix that's basically a sum of cliques. Okay, and you say here's a matrix, and what it consists of is a sum of submatrices. Okay, where each submatrix is specified in a given position, like 5, 10, and 11. 5, 10, and 11. What this means is I want to take these entries here, okay, in rows in the intersection of rows 5, 10, 11 and columns 5, 10, 11. Those 9 entries, I want to add updates to those 9 entries. And so you'd have a little loop over here which iterate across all 9 entries and then insert them in this matrix. So that's one common way of creating a matrix. Well, this is very, very awkward to do with the compressed column form. It's very awkward to take a matrix that's stored column by column and just add entries to it arbitrarily. Okay, because they're all so packedly tight together. So this is where the triplet matrix comes into play. And it's much simpler to do this. So what we want to do is just have the column indices, the row indices, and the numerical values. So it's actually 3 arrays. And we've got some empty space here at the end. So we have NZ max, the largest, the size of the 3 arrays, but we have NZ that tells us where we are right now. And that's the triplet matrix. And this is why. Now you see the reason why I want to have a matrix with some slack in it. That's what these have. When you insert the 5th entry, you've got 5 entries and then some slack. And the reason you have slack is to make this dynamic. It's a theoretical problem. It's to make this dynamic table algorithm work. You have to have the slack to get the correct time complexity. So the slack is very important. So that's what this algorithm does here. Then this is an implementation of the dynamic table algorithm, where the table is growing, the list is growing dynamically. So what I do here is I start with a triplet matrix. I call it T. It's just the same C-sparse data structure. And what this is doing, it's saying, hey, I've got a new scalar, x, and I want to add this triplet in entry. I want to add an entry to row I, column j. So in other words, what this one call is doing, it's doing Aij equals Aij plus x. You don't see a summation here, though. Because if Aij is already in the matrix and you have duplicates, the interpretation is that the actual value of Aij is the sum of all the duplicate entries. So they just add up. And that's useful because, for instance, finite element methods, when you're adding up these finite elements, they can overlap, and the overlap you want to add. So, a very common thing is just to add the duplicates. Yeah.
Maybe getting ahead here. Is there a way to just say aij equals x?
Not really, actually. Think about it. It'd be tricky. You'd have to know that it's already there or not.
Yeah.
Now, one thing you can do is you can try to do that, and then if you fail, well, when you convert this into compressed column form, a value will be returned back as to how many duplicates you actually had. And if you expected none and you got some, you know you did something wrong. Otherwise, you have to do some kind of search. You know, if you want to assert that, it's very difficult, very painful, asymptotically speaking. So the first thing, again, is this guard to say, hey, look, does this triplet matrix even exist? Okay. And by the way, I should say, if you're going to watch this presentation offline, and you have a hard time reading the slide, all the slides are on my webpage. So you can watch me and then have another window up to your left or right or whatever, and you can actually see the slide, and then you can see where I'm pointing to. Okay, so the first thing is a guard to say, hey, do I have a matrix after all? First of all, it has to exist, T has to be non-null, and it has to be a triplet matrix. You can't call this function on a compressed column matrix. It'll return a failure. And I also assert that the row and column indices have to be greater than or equal to 0. If they're negative, I'll return a failure. I don't require that they be upper bound, that there be upper bound on this matrix. What if, in fact, you don't even know the size of your matrix to begin with? Well, the triplet matrix doesn't care. It says, fine, I'll just make my matrix big enough to hold it in terms of the row and column dimensions. The row and column dimensions of the triplet matrix are just two scalars. They have nothing to do with the size of the data structure. So it's no big deal just to make them bigger as needed. The next thing is a one-liner that does the dynamic table. First of all, then I ask the question, well, is my NZ greater than or equal to NZ max? In other words, am I out of space? If this is true, then C will evaluate the next expression. In particular, it'll evaluate the Sparse. And here's the doubling, twice the existing number of non-zeros. This is another reason why NZ max had better be at least 1. If it's 0, this twice 0 will still be 0. So it's very convenient to have an object of some size that you can double. You can't double nothing. Double of nothing is nothing. If the Sparse fails, I return failure. So this both checks for space and reallocates and checks to see if the reallocate succeeded in a single line of code. This is one reason why the whole package is just 2,200 lines of code, is these terse one-liners. Right? They can be kind of terse, hard to read sometimes, but anyway, there you have it. One thing you'll note that I did not do is a second line of code here. I did not say, for example, okay, let's get ti equals ti of t of I. I didn't do this. And the reason I didn't do this is because the Sparse might change that. I could have done it in the next line, but I guess I just didn't. For this particular code, like right here. Okay, so here's a snippet of code of how you would create a triplet matrix. You'd allocate of size some NZ, and this tells you, let's see, whether or not you want values, and this tells you something else. I forget what the two Sparse did. One was asking for numerical values, and the second one. Oh, yes, right. The next one was a triplet matrix, not a compressed column matrix. Thank you. Then we might be creating a pattern matrix. If we are, then Tx will be null, so we skip this step. And here we just insert the entry, increment NZ, and return. So this does the dynamic table algorithm. Very simple little algorithm, but it relies on this. It implements this algorithm here, the dynamic table. And it all works very smoothly because of the Sparse wrapper. It does all the right things for you. It makes sure that when you reallocate 3 objects, that all of them get reallocated to the right size. So now what I want to do, and I'm going to run out of time because this is going to take more than 5 minutes to do, is I want to now take, after I've created my triplet matrix, filled it with all the entries, now I just have a bag of entries. All right, it's the triplet form. And there's not a lot you can do with the triplet form matrix. You can do things like matrix vector multiply with a triplet form, because there it doesn't matter what order you go through the entries. Even with their duplicates, it doesn't matter. You can just loop through all the entries and just use them in the multiplication. It works. But most algorithms find it very awkward just to deal with a matrix as an unsorted, unadded, unsummationed, that's not a word, unsummed bag of entries. And so we want to then convert this thing to a compressed column form. So let me give you the algorithm, and then we'll look at the code next class. The idea is a bucket sort, right? So I want to take these entries. For the moment, I'm going to ignore duplicates. Any duplicates then will just fit in the same column. And so any given column now may have duplicate row indices. But what I need to do is I need to create a bucket for column 0. And if you will, how do you like me to draw the buckets? Draw them this way, maybe? Okay, I'll draw them this way because they're columns, right? For me, it doesn't matter because this looks the same thing as this. So sometimes being dyslexic actually helps because you can look at the algorithm another way and say, oh, yeah, I see how it works. And anyway, so whichever, let me draw it this way. So what we first have to do is go through this triplet matrix and count how many entries are there. How big are each bucket? How many entries go in each column? So that will take time, order nz, to simply do the count. Count the number of entries in each column. Remember, I'm ignoring duplicates, treating them as separate entries for the moment. So column 0 now, I know how big it will be. In column 1, I know how big it will be. In column 2, and column 3, and so forth. Down all the way down to column n-1. Now that I know that, I can now compute my column pointers. AP of 0 is always 0. The first entry always starts out at the first position. Okay. AP of 1 is always the number of entries. It's always AP of 0, which is 0, plus the number of entries in column 0. Right? Like if there's 5 entries here, then AP of 1 will be 5. And so in general, AP of j is always equal to AP of j minus 1 plus the number of entries in column j minus 1. So I need to do a cumulative summation of the number of entries in each column to get these column pointers. So now I have column pointers pointing to the topmost entry, the first entry, not necessarily the first row index, but the first place where I've got empty space now. This is all empty. There's nothing in here. So first you do the count. Next you do the cumulative sum. And the next thing you have to do then is to go through over the triplets, and place them in the buckets. And when you place them in the buckets, suppose I've got I see an entry, I'll call it T, Tij. Well, I need to go to column J of A, and I'm going to have to keep track of entries I've already inserted into the column A, and then the empty space. So I've got here, this is AP of J. I don't want to lose track of what AP of J is, but I need a pointer here, or an index, to tell me where do I put the next thing. And that's where I'll put row index I, and then whatever the numerical value is will go right here. This, of course, is two arrays. It's the row index and the numerical value that has to go in these two. These are really 2 arrays. And then this pointer will have to increment. And when you're done with this, you'll have a matrix filled with entries. And so what I'll do next class then, and I think I'm just exactly out of time, is I'll walk through here. You can see the different steps. There's the allocation of some workspace, of the output matrix and some workspace for this extra pointer to figure out where we currently are. There's the cumulative sum, and there's walking through all the entries, and this is a very terse thing that puts it in the right place and increments. And then when we're done, we've got a compressed column matrix, but potentially with duplicates and potentially with row indices that are unsorted. They're out of order, and if we want to sort them, we've got to do something else. If we want to get rid of duplicates, we've got to do another pass over this matrix. That's another thing. Then removing duplicates in each column and then sorting the row indices if we want is yet another step. So with that, I'll leave it at that. Again, look at the code, run the code in MATLAB, get the demo up and running, and I'll see you Friday. Thank you.